Hello, in this video I'll be giving a high-level summary of a presentation we gave at EGU 2023, in which we provide an overview of ongoing work at Fathom related to the creation of a global flood inundation event set. So the background to this work is that global flood maps, such as those produced by Fathom, are extremely useful, giving insight into the frequency of flood depth exceedances anywhere in the world. But they say nothing about what unique events look like. Yet it's essential to many end users to know just this. Reinsurers, for instance, with portfolios spanning vast regions, may need to know what their potential event loss could be from large, rare events. One could use historical records to start to answer these questions. However, typically observations cover a relatively limited time span, perhaps 30 years, meaning that we're unlikely to fully capture our true risk based purely on observations. One solution to this problem is the creation of a modeling framework, typically trained on historical observations, which can be used to provide predictions representing thousands of years of events. Here we provide a high-level overview of the ongoing work, which aims to use global, freely available datasets to produce a 10,000-year synthetic flood event set accounting for pluvial, fluvial, and coastal inundation processes. So the first step in our modeling framework is the collation of global reanalysis datasets. In this research, we use ERA5 precipitation, Codec GTSM coastal water levels, and GLOFAST discharge predictions, the latter two of which are forced by the ERA5 reanalysis products. All datasets are available globally and span 1980 to 2018 time period. The key task at this stage, once data is collated, is to extract historical events from these datasets. In our research, we use a simplistic spatial and temporal window to define events, and we extract these events by using a series of spatial temporal clustering steps. The outcome of this process is a table that tells us what is happening in every modeled site within each unique historical event that we defined. The event table produced acts as our training data in the next stage of the model development, the construction of a dependence model. Here we use an adaptation of the model first proposed by Heffernan and Torn in 2004. For full details, I'll refer you to the related publication section, but in summary, here we define relationships between every pair of sites within our training data, each of which informs us what the likely state of a site is, given the conditions at a conditioning site, which is experiencing an extreme event. The top image in this panel provides an example of what we hope to see in these constructed relationships. Here we plot the probability that any other site is experiencing an event, given that a specified conditioning site is experiencing an event. In both examples, we see a clear spatial structure to dependence. As you might expect, as one moves away from the conditioning site, we see a lower likelihood that a site will be extreme. Below this, we provide a localized example of the model. Here we have our conditioning site in red, and two neighbors at varying spatial distances from that site. The scatter plots show the observed relationship between these points in blue and the model relationship red behind it. This example demonstrates that the dependence model appears to be able to recreate and expand upon what we've seen in the past, in cases where there's both strong and weak tail dependence. The outcome of this methodological step is a characterization of our dependence model. This provides us with the ability to say, for any event conditioned on any given site, what do we expect to see happening at every other site? So using our dependence model, we can start to generate synthetic events across our modeled sites. As we require information everywhere, not just at points, we discretize our regions into unique catchments and interpolate our synthetic events across them. To obtain the corresponding inundation depths, we sample catchment by catchment from Fathom's existing global hazard layers, stitching together a complete flood map. Flood maps are provided for each peril, for each event, and the maximum depth in each pixel is retained. The outcome of this stage in the process is the creation of 10,000 years of event flood maps. This, then, is our flood event set. In the final panel, we provide an example application from a recent paper that attempted to characterize flood risk in the UK. This image shows why it's important. The dashed lines represent observed losses, ABI, and two deterministic losses from other publications. The histogram represents 10,000 iterations of 20 years of losses from our synthetic event set. The key here is that it clearly shows a deterministic view of loss, e.g. one based purely on history, only gives you part of the picture. Here we show that the expected annual damage within the UK for the last 20 years could have been anywhere from approximately 300 million to more than 1,500 million. Understanding this uncertainty is essential, and these models should help end users to do that. So the next steps in this research include further development of the event set framework, as well as the collation of global exposure and vulnerability datasets, which, when complete, will form the basis of Fathom's first global flood cat model.